Now, since we have talked about the kinetic theory of gases, we would like to understand what the kinetic gas equation is and what all can be derived from it, right? So, the kinetic gas equation says that PV is equal to 1 by 3 mn u square, where P is the pressure, V is the volume, m is the mass, n is the number of molecules, m is the mass, n is the number of molecules, okay, and u is the RMS speed. Now I'll tell you what RMS speed is in some time, but just remember that the u we are talking about here is the RMS speed. So this equation can be rewritten as 2 by 3 times n, okay, and like what we've done is we've taken n out, okay, and we have multiplied and divided by 2. Here we have half m u square. So if you look at this expression, half mu square, it looks somewhat like the expression of kinetic energy, isn't it? So let's write this down as 2 by 3 times n times the kinetic energy. But this kinetic energy is of one molecule. Why? Because the mass here is of one molecule and the velocity is the URMS. So if we multiply the kinetic energy of one molecule by the number of molecules, we can say that this is equal to the total kinetic energy of the mixture or of the sample. So the expression becomes basically that Ek, which is the average kinetic energy of the sample, is equal to 3 by 2. We've sent the 2 by 3 to the other side, PV. And we know that for an ideal gas, the equation is PV is equal to nRT. So substituting PV for nRT, we can write that this is equal to 3 by 2 nRT. So the average kinetic energy for 1 mole, that is the value of n, would come out to be 1. And so the expression for 1 mole would be 3 by 2 RT, where we have a sample of the gas. So this is the average kinetic energy of the sample when 1 mole of it is taken. Or we can call this to be the kinetic energy of Na molecules, right? 1 mole implies Na molecules, where Na is the Avogadro's number. Then what will be the kinetic energy of 1 molecule? Simply using the unitary method, that for Na molecules, the kinetic energy is 3 by 2 RT. So for 1, it would be 3 by 2 RT divided by Na. So here we define another term which is R divided by Na and is known as the Boltzmann constant. So it is represented as Kb, okay, where we can write that Kb is equal to R divided by Na. So this is basically the kinetic energy per molecule, which is 3 by 2 kBt. And the value of K, since R is a constant and Na is also a constant, the value of K comes out to be 1.38 into 10 to the power minus 23 joule Kelvin inverse. So we can write that its units in the proper system will be m L square T minus 2 and K inverse, right? Where MLT are the mass, length and time and K is the unit for temperature. So here we have derived the expression for the kinetic energy in terms of the RMS speed. So now we'll try to know what is the RMS speed or what are the different kinds of speeds that we define for a given gas sample. So the first one is the average velocity. The average velocity is, as the name suggests, is the weighted average of all the velocities. So let's say in the sample we have n1 molecules with velocity u1, n2 molecules with velocity u2, n3 molecules with velocity u3 and so on. And we know that there is random motion, so different number of molecules can have different velocities. So the average velocity, let's write it as V average, is defined as n1 u1 plus n2 u2 plus n3 u3 and so on divided by n1 plus n2 plus n3 and so on. So if we write it in summation terms, we can say that summation NIUI, where I varies from 1 to n, where n is the number of particles, divided by summation Ni, where I varies from 1 to n. This is the average velocity. And another expression for the average velocity is root 8 RT divided by pi m. Try to remember both these expressions, these are very important. Then we come to root mean square velocity, or what we were referring to as VRMS. The same conditions, the same sample. We'll first break the name root mean square so that we can understand what it actually means. So root mean square is the root of the mean of squares. And we'll start from the back. Squares, first of all, the squares of the velocities. So if n1 particles had u1 speed, n2 had u2, n3 had u3, the squares of the speeds will be u1 square, u2 square, u3 square, and so on, right? So mean of the squares would mean that if n1 particles have u1, n2 have u2, n3 have u3, and so on, divided by the total number of particles, right? This will be the mean of the squares of velocities, correct? And over that we have to put a square root. So this gives us the expression for the root mean square velocity. So if we write it in summation terms, we can write it to be the square root of summation NIUI square, where I varies from 1 to n, divided by summation Ni, where I is again varying from 1 to n. And this is also equal to root 3 RT divided by m, where m is the molar mass. These two expressions are also extremely important. Now the third one is the most probable velocity. By definition and by name, we can guess what it would mean. The most probable velocity means the velocity possessed by maximum number of particles in a sample. That is the most probable velocity. And V most probable is defined as root 2 RT divided by m. And if we're talking about, say, 1 mole of a gas, okay, we can say that PV is equal to RT, and therefore V most probable will be equal to root 2 PV divided by capital M. And similarly for all of these, the root mean square can be written as root 3 PV divided by M, and average velocity can be written as root 8 PV divided by pi m. Now let's see a representation of these velocities on something which we call as the Maxwell's distribution. What is the Maxwell's distribution? Maxwell's distribution curve is a curve which represents the fractions of the particles on the y-axis and the speeds on the x-axis. So in a given sample, we had studied that all the particles have random velocities. So there can be a range of velocities from 0 to tending to infinity. Like there's nothing is real infinity. So therefore from 0 to something tending to infinity. And in that entire range, that is this entire x-axis, all the velocities are present inside the sample. However, their frequencies or the fraction of the molecules possessing those velocities can be different. For example, if we talk about this point, the velocity at this point is here and the fraction possessing is this one. And if we talk about this point, the velocity is this and the fraction is this. So at different velocities, different fractions can be obtained for the sample. So basically the three velocities which we just studied, that is V most probable, V RMS and V average, these three are also represented somewhere on this line. So by definition, V most probable should correspond to the peak, this peak. So the white graph which you can see here refers to the V most probable. That is, it is having the maximum fraction of molecules corresponding to this speed. That is why it is named as the most probable velocity. And then if we talk about V RMS and V average and compare their expressions, we can say that V RMS is root 3 RT divided by M and V average is root 8 RT divided by M. Now 3 is definitely greater than 8 divided by pi, right? So therefore V RMS should be greater than V average, and V most probable was root 2 RT by M, and it is the smallest of the other two. So therefore the white one represents V most probable, followed by the blue one, which is V average and is represented as V bar, followed by the orange one, which is V most probable. So this is the representation of all the three speeds on the Maxwell's distribution. Also, in the Maxwell's distribution curve, the area under the curve, which is the part I am shading, this entire area represents the number of particles in the sample. So the integration under this curve would basically provide us with the total number of particles which are present. And if you think, the total number of particles should remain constant, right? I call it as n total. It should be a constant. And we also know that from kinetic theory of gases, as temperature increases, the kinetic energy should increase. That is, the V should increase, which implies that the V most probable should increase. And if V most probable increases, it implies that this peak should shift, right? If this is V most probable and the higher one is here, the peak should shift. So if we look at this curve, at 100 Kelvin, the peak is corresponding to this point. However, at 200 Kelvin, the peak has shifted. At 500, it has shifted further, and at 1000, it had shifted even further. So what is happening is that as the temperature increases, the peak of the curve shifts. However, since the number of particles, that is the integration under the curve, has to remain a constant, therefore the curve also flattens because it shifts a bit forward to keep that integration under the curve as a constant. To understand that, we can say that, say in the 100 Kelvin and the 200 Kelvin curve, this region is what we can see as something extra in the 200 Kelvin curve. However, this is the region which has been deleted because of the shifting. So both of these regions balance each other and keep the number of particles as same. That is why there is a drop in the curve. So we can also conclude one thing, that as the temperature increases, the V most probable increases, but the fraction of molecules possessing it decrease, right? At 100 Kelvin, this was the fraction, but at 200 Kelvin, the fraction of molecules has decreased, okay? So these are a few important results about the Maxwell's distribution curve.